Hello, class. So in this video, we're still in chapter 4. Again, we're covering sections 4.1, 4.2, 4.3, and 4.4, all in this one lecture. Okay. In the previous video, we saw how all of the theorems that we know generalize to the nth order case, right? All the theorems that we know for linear ODEs, right, generalize, particularly the existence and uniqueness of an initial value problem, right? The existence of a fundamental set of solutions for the homogeneous case, and then how to find the solution when the nth order linear ODE is not homogeneous, right? Find the complementary solution, right? The solution for the homogeneous case, and then find a particular solution for the original ODE and add them together, right? So everything generalizes the same way as in the previous sections when we were looking at the second order ODE case, linear ODE case. Now let's do an example, right? So find the general solution to y triple prime plus 3y double prime minus 4y equals 0. Right? So this is third order linear constant coefficients. So what do? We have to look at the characteristic polynomial. So P of R is going to be, remember that again, the power of R is always the same power of the derivative. Right? So R cubed plus 3y, R squared, R squared minus 4R, minus 4 equals 0, right? Because y is the zeroth derivative, right? So again, the power of R always matches the power of the derivative. Okay. Oh, I don't want to set it, yeah, we're going to set it equal to 0, of course, but for now, this is just a characteristic polynomial, right? Now, what do? We know that in order to get solutions, we have to set this equal to 0, right? So we set R cubed plus 3R squared minus 4 equal to 0. Now, you already are, if you haven't noticed already, you're going to start to notice the problem with these sort of questions. Second order linear ODEs are nice because we have a very easy formula to write the roots, right, of a second degree polynomial. There are actually also formulas for third and fourth degree polynomials. They're just very messy. And if no one has told you, then let me tell you now, let me break your dreams, but there's no closed formula. There's no way to write solutions or roots of fifth degree or higher polynomials in terms of radicals, right, in terms of square roots. It's not possible. It's very hard to show that that's the case, but there's no way. That's why there's no formula for the roots of a fifth degree, sixth degree, etc. polynomial. There are formulas, again, for 1, 2, 3, and 4, nothing for 5 or above, because no such formula exists. If you study mathematics and then you study group theory, you're going to see why that is the case. Right? I'm not going to get into it because it's very complicated. But, again, specific for us, it is a problem because the formulas for degree 3 and degree 4 polynomials are kind of complicated to work with. You can go ahead and look them up and find what the roots are, but I won't do that in this example. Instead, what we're going to do is say, okay, it's third degree. If I can find at least one root, then I can write this as a second degree polynomial. Okay? So times this one root. So let's try to find one root by just guess and checking. So let's find an R that makes this 0. And I think R equals 1 works because let's see what happens. 1 cubed is 1 plus 3R squared. So 1 plus 3 is 4 minus 4 is 0. So R is one of the roots. R equals 1 is one such root. So given that R equals 1 is one of the roots, how do we rewrite this third degree polynomial as a second degree polynomial times this root? Well, you have to use polynomial long division. So let me show you an example of polynomial long division. This is going to be a lot of algebra review right now. So the root is R equals 1. So remember, you write that as R minus 1. So we're going to divide R cubed plus 3R squared plus 0R minus 4, we're going to divide this by R minus 1. Okay, so why do we have to multiply R? In order to get R cubed, we have to multiply it by R squared. So multiply everything by R squared, we get R cubed minus, so R squared times 1 is R squared, subtract. So it's the same thing as long division, right? You're just doing it with polynomials. Subtract, so r cubed minus r cubed is 0. 3r squared minus negative r squared. So negative becomes positive, so you get 3r squared plus r squared is 4r squared. And then you bring everything else down. So plus 0r minus 4. Okay. How many times do we have to by what do we have to multiply r to get 4r squared? Well, we can multiply by 4r. So plus 4r. Multiply everything by 4r. 4r times r squared times r is 4r squared. 4r times minus 1 is minus 4r. And as before, subtract. 4r squared minus 4r squared is 0. 0r minus negative 4r is 0r plus 4r, which ends up being positive 4r. So it's 4r here, and break down the 4. How many times do you have to or by what do you have to multiply? I'm trying to do it in the just usual division, where you would say how many times does this go into this? But here you want to say by what do you have to multiply r to get the leading term here. Right? That's what we're trying to do in each step. Trying to multiply the leading term in whatever we're dividing by, which in this case is r minus 1, to match the leading term of whatever we're trying to divide. Right? So in this case, we're trying to match r cubed. This is we're trying to match 4r squared. Now we're trying to match 4r. So what do we have to multiply r by to get 4r? Well, by 4. Right? So plus 4. Multiply everything by 4. Right? So 4r, and then that minus 1 times 4 is minus 4. Subtract. 4r minus 4r is 0. Minus 4 minus negative 4 becomes minus 4 plus 4, which is 0. So what does this mean? This means that we can rewrite r cubed plus 3r squared minus 4 as r minus 1 times r squared plus 4r plus 4. So that's one method to deal with third or fourth degree polynomials, right? Or higher degree. Try to find enough roots until you get it to a degree, and then divide by those roots as many times as needed until you get to something that's second degree, because we have an easy formula for that. Again, if you don't want to do this, you would have to look up the third degree formula, right? So the roots of third degree polynomials, whatever that formula is. So now, so we know what one of the roots is. Again, all we did was rewrite the characteristic polynomial like this. So what are the other two roots? Well, we need to find the roots of r squared plus 4r plus 4. And I think that factors as r plus 2 times r plus 2. Right? So you can verify that. So this is the same as r minus 1 times r plus 2 times r plus 2. It's just r plus 2 squared. Okay, so we found all of the roots of the characteristic polynomial. Right? We have roots. Right? The roots are r equals 1, and then r equals negative 2 with multiplicity 2, right? Because we have 2 of them. Now, how do we get 3 linearly independent solutions, right? This is a third degree, a third order ODE, so we need 3 linearly independent solutions. Well, we can write 2 of them, right? We know from the work we did for the second order that if we have 2 roots, right, then we know that at least 2 solutions, right? We have y1 equals e to the 1 times x, which is e to the x. We have y2 equals, so r is minus 2, so e to the negative 2x. Right? How do we find a third one? And again, they have to be linearly independent, right? We know that these 2 are linearly independent. Right? You can do the Wronskian, but we've done that work before for the second order case. How do we find a third one? Well, basically, this is the trick. Whenever you have a root of more than, so if all the roots are distinct, we can find n linearly independent solutions, right? Just e to whatever root times x. In the case that you have that you don't have all of the roots being distinct and you have multiplicities bigger than 1 like here, then it's still very easy, right? Well, you always get at least 1 root from whatever root you have. You still get at least 1 solution from each root. We already wrote that one as y sub 2. And how do you get more? Well, just multiply by x. Right? And you can verify using the Wronskian that all of these solutions are linearly independent on I equals all real numbers. So let me write are linearly independent on negative infinity to infinity. So what's the general solution? Is C1 e to the x plus C2 e to the negative 2x plus C3 e to the negative x times e to the negative 2x. Right. So the idea is whenever you have a root of multiplicity more than 1, write the solution that you get, right, like we did in this case, and then multiply by x. So let's say you have something of multiplicity 5, and I think I'm going to talk about it in the next. Yeah, okay, I did talk about it later, right? So in this example, we multiply by x once, right? Whatever root you had of multiplicity bigger than 2, whatever solution you got from that, greater than 1, sorry, multiplicity greater than 1, whatever solution you got from that, we multiply it once by x to get another solution. What if we had a root of multiplicity 5, right? How do we get 5 linearly independent solutions from one root? And the idea is this, just multiply by x. Right? So if we wanted to get another, so this were, let's say, a root of multiplicity 3, we would have another solution that would look like x squared times e to the negative 2x. Right? And that's what I'm going to do in this note. Right? So in general, if we have a characteristic equation corresponding to an nth order homogeneous ODE, right? So this would be the characteristic equation. Right? The characteristic polynomial would be a sub n, r to the n, etc., equal to 0. Where the a sub i's are reals, right? We only work with real coefficients. Right? Now, if all of the roots are distinct, then we know what the general solution is, right? Just take a linear combination of exponentials. Whoa, what happened here? Yeah, I don't know what happened there. It should just be C2 times e to the R2x, right? We know that you just take a linear combination of exponentials with exponents being the root times x, right? And I'm just going to tell you that this works for all real numbers, right? You can check if you want using the Wronskian, but since there's more, in this case, there's going to be more than 2 functions, right? The Wronskian is going to be a big matrix of 3 by 3 matrix or 4 by 4. It's going to be larger than 2 by 2. Right, so the only way you could find what that Wronskian is by using Mathematica, which I am going to show you how to do that. Right? Right, but so in the case that all of the roots are distinct, it's easy to find the general solution. If, however, we have a root of this equation, so a root of 3, with multiplicity k, right, with k greater than 1, right, if k is 1, then it's fine. Right? So if we have a root with multiplicity k greater than 1, like we had in the previous example, the root negative 2 had multiplicity 2. So k greater than 1. We can show that e to the rx, comma, x times e to the rx, comma, x squared times e to the rx, comma, all the way to x to the k minus 1 times e to the rx are linearly independent solutions to the original ODE. So here I wrote 2 because of the previous notes. So 2 is the original, right, ODE. So it would be a sub n. So these are all constants, right? So a sub n, yn plus a sub n minus 1, yn minus 1 plus a1, y1 plus a0, y equals 0, right? Okay, so again, if we have a root of this characteristic polynomial of multiplicity greater than 1, then you can always get k linearly independent solutions from a root of multiplicity k, right? How do you do it? Well, you start with the original one that you get, right? So you know that you always get e to the rx, where r is the root. You still need k minus 1 other solutions, right? Because it's multiplicity k. Well, how do you get the k minus 1 other ones? Well, you just multiply by x to get the next one. Multiply by x again, you get the next one, etc., all the way until you have k linearly independent solutions. And you can show that these are linearly independent always for all real numbers. So the idea is, if you have an nth order ODE, you want to get n linearly independent solutions, right? So if a root has multiplicity k, you want to get k linearly independent solutions from that root, and this is how you do it. So I'm going to do an example, I think, in the next video about this. Yeah, I am going to do an example. So, but that's the idea. You just multiply by x as many times as you need until you get as many solutions as the multiplicity of the root. So let's do an example. So suppose the homogeneous ODE, right, and remember we're only working with constant coefficients right now, has characteristic equation r minus 1 plus I times r minus 1 minus I times r cubed equals 0. Find the general solution. Okay, well, we have two roots that we know, right, that are given immediately, that are multiplicity 1, and these are complex. So remember, in the case that you have distinct complex roots, and the complex roots are always going to come as pairs, right? Meaning that if you have, if a plus bi is a root, so is going to be a minus bi, right? So these are always going to come in pairs. Right? So in this case, a equals 1, b equals 1. So they always come in pairs. Okay? So from these two roots, we know how to get two linearly independent solutions, right? How do we do it? We took e to the whatever the part that's not multiplying I is, in this case 1, times cosine of the part that's multiplying I, in this case is also 1, times x. That was one of them, right? And then you do the same, but you replace cosine with sine, right? And this comes from the two distinct complex roots, right? You just find what your alpha is, find what your beta is, which here are called a and b. We can call them alpha and beta. Right? And then we know what sort of roots we get from those, from the work that we did in previous sections. Okay, so we have two linearly independent solutions. We need 5, because this is a 5th order ODE. So we look at the other root. We have a root r equals 0 of multiplicity 3. Right, so we have a root r equals 0 of multiplicity 3. As I mentioned, we want to get as many solutions as the multiplicity of the root. Right, so here we had a root of multiplicity 1, we got one solution. Root of multiplicity 1, we got one solution. We have now a root of multiplicity 3, I want to get 3 solutions. Right. How do we do it? Well, by the previous note, right, write down the solution that you know. Right? You know that this is always a solution. Right? Just e to the whatever, since this is a real number, it's just going to be e to the root, in this case 0 times x, which is going to be just 1, right? Because e to the 0 is 1. Okay? That's one solution. How do we find the other two? Again, this is a root multiplicity 3. We want 3 linearly independent solutions. So how do we find the other 3? Well, by the note, just multiply this solution by x as many times as you need until you get how many solutions you want. Okay. So we want 3 solutions out of this root. We have 1, right? So let's multiply by x to get another one. So 1 times s is just x. Now we have 2 solutions coming from this root of multiplicity 3. We want 3 of them. Okay. So just multiply by x again. Right? Just multiplying by x as many times as you need until you have enough solutions. Okay. Now we have a root of multiplicity 3, 3 solutions, and we're done. And these solutions are always going to be linearly independent for all real numbers, always. And I think I made a note of that here. Yeah, they're always linearly independent for all real numbers. So you don't have to worry about that. So now you have 5 linearly independent solutions for a 5th order ODE, so you know what the general solution is. Goes C1 times Y1. Right? I'm just going to write like this. Just write it the whole way. Why not? Times e to the x cosine x plus C2 e to the x sine x, right, plus C3 times Y3. Well, Y3 is just 1, so it's just plus C3. Oops. Plus C4 times Y4. Y4 is x, plus C5 times Y sub 5, which is x squared. Right? And again, this works always for all real numbers. So it's basically as simple as that. If you get a root of multiplicity bigger than 1, just write down the one that you always get, right? E to the power of the root times x, and then just multiply by x as many times as you need until you get as many solutions as the multiplicity of the root. And that's the idea. That's how you deal with the linear constant coefficients homogeneous case when you have a higher degree than 2. Right? This is the idea. Okay? Now, in the next example, we're going to see how to do method of undetermined coefficients when we have a higher order ODE, higher order than 2. But it's basically the same. It's the same thing that we just did. We just have to then write the guess. The guess of the particular solution works exactly the same way. So really the only new thing is this. So we're going to do that in the next video.